what if I want to keep making this more accurate? What if I wanted to use, maybe not 2 subintervals, let's start using, I don't know, let's use 4 subintervals. What do you think we're going to have to do? Split into 4 different things, right? But obviously we don't want to have to just kind of keep writing this out and keep drawing this out. There's got to be a bit of way. So like when you said the small changes in x? Yeah. So we could think about it like that, right? We're splitting up into smaller bits, right? Think about what's actually going on when you're doing this calculation. You're going to be doing a lot of these trapeziums, and you're going to be constructing them all up. But you notice here how we use the 1 twice, right, in both of these calculations, right? There's a bit of an overlap there, right? So these endpoints here, when you think about them, these endpoints, you're only using them once, right, because they're on the outer parts. But the ones in the middle, can you see how you're actually going to use each of those lengths twice in your formula, right? So there's an easier way to write this, and there's a formulaic way of writing this, and the way to do that is this. So rather than trying to think about trapeziums and do that, there is a formula that we can apply, and the formula looks a bit like this. The integral of f of x from a to b is approximately equal to h on 2. Now, because we're only using like the first one once, that's f of a plus, now all of these lengths we're going to be using twice because all these trapezium overlaps, right? So it's 2 times f of, we'll call this like the first point there, afterwards would be x1 plus f of x2. And we say up to whatever the second last one is, we'll call that f of x n minus 1. And we have this last one over here, we'll call that f of b. So this is like the formal kind of trapezoidal rule here, right? Now just to make a note, one more thing. This h value, on your formula sheet, it's written slightly differently. So it's written as b minus a on n, because it actually depends on how many subintervals we want, right? Because remember how if we split it up here, each subinterval, because I had 2 subintervals, each one was length 1, right? But if I'm going to be splitting it up into 4 subintervals now, what's each of my lengths going to be? I want 4 of these trapeziums, right? So what would the height of each trapezium be here, in this case? Because before I only had to split it up once, but if I want to split it up like 4 times now, right?
Are we going to use induction on it now?
No, we don't need to do that. We just want to think about, like, it's this topic here, right? Let me just make it as a precursor. It's not like a full-on mathematical kind of thing. It's just thinking geometrically, like shapes, right? So we really want to emphasize this idea of shapes in order to evaluate integrals, right? So think about it this way. We found out that to approximate, I can use this method to do it. But if I want to be more accurate, I can increase the number of trapeziums, right? So over here, that's what I'm going to do. So from 0 to 2, right, instead of just having 2 trapeziums, I've split this up. I've got 4 of them now, right? But when I do that, I make the height of each trapezium smaller. What's the height of each trapezium now? Because remember, I said I have to make them equal, right? Each of these segments, yeah? So what I'm saying is, so from 0 to 2, if I want 4 trapeziums, and they have to have equal heights, what am I really doing there? Like, what's the height of each of these going to be? They are the same height, yeah. No? Is that not making sense?
Like width is height.
Yeah. So remember how I emphasized that, like, the height of each trapezium is this particular length there? Yeah.
That was a little bit long.
Sorry, yeah. So if you want to think about width or height, yeah, either way, right? So is that making sense what we're trying to achieve here? We're trying to, like, increase the accuracy of this by...
To make them even.
Yeah, that's right. Yeah. So how would we do that? Yeah, we divide by the number of subintervals that there are. And so that's what this n is. That's what this n represents, the number of subintervals. Yeah. So what I do is I'll take, okay, what's my b and a? They're like your end values, right? So b minus a. So it's like 2 minus 0 divided by how many subintervals there are. So my h is going to be equal to 2 minus 0 on 4. And that's just going to be half. And that makes sense, right? Because each of these is half. Can you see how you'd split it up evenly like that? It's 1.5, 2, right? And then you can think about using this formula over here. And the way to construct that is, this is I'm going to introduce a table. And this is the way you want to lay out all your questions that involve trapezoidal rule, right? So if I have an x value and the function value. So the x values are going to be all the ones that I have over here along the x-axis. So that's just 0, half, 1, 1.5, and then 2. And then your function values are, okay, I'm going to take this and I'm going to substitute it back in to your original equation over here. So do you want to go ahead and find them for me? Just substitute them in. Your function values for me?
Yeah.
What do you got?
So 0.
Yep.
1 on 8. 1. 27 on 8. And 8.
And 8. Okay, sweet. And then what we'd do is we'd apply the formula here. Because what have you got here? You've got your h value, right? We know that that's just half. And then we'd have to think about, if you think about your trapezoidal rule formula, like that's why we have this h12 here, right? It's the same idea. We're just kind of merging all these formulas, all these applications together, rather than having to write them out individually each time. We're just putting them all together now, right? So I've got it as one expression here, and so my h value was half. So I'm going to get the integral is approximately equal to. So what is this? This is from 0 to 2 x cubed. That's approximately equal. So I'm going to use those two dots here. Approximately equal to. Yeah, 1 over half on 2, you can put that in your calculator. Yeah, which is 1 on 4. And then we're going to write, okay, this first function, so f of the first one here, so 0, plus all these ones. Remember, because they're inside here, I'm actually using them twice in the calculation. So it's going to be 2 times all of these ones here. Sorry, all of these, it has to be the function values, right? So 1 on 8, plus 1, plus 27 on 8, and then plus my last. So the way I think about it is I see this as, okay, we've got, man, this pen, I've got to stop using. So this is like f of the first value, and this is like the last value here. And there should be brackets around this too. And so when you put that into your calculator, you're basically approximating what this integral is going to be. And the idea is that the more subintervals you do, the more accurate this is going to be. Right?
I mean, what if we actually integrate?
Then you would get it wrong. Because the question would say use trapezoidal rule to actually evaluate this. It's a good question. Like, why do we need to do that, right?
Just get your answer and then make it slightly.
And then like add 1 to it, add or take away 1 from it. What did you get from that?
17 on 4.
17 on 4. Don't know. Alright, so anytime we get a question which is asking us to use the trapezoidal rule to approximate something, you have to use it, right? You could just integrate this. You know what this becomes. This has become a logarithmic function, right? But if they say use the trapezoidal rule, we have to apply this method. And the thing you want to look out for is how many subintervals are they asking you to use? In this one, I'm going to get you to, again, use 4 subintervals. Right? So how do we draw this out? So the idea is that, first of all, okay, to draw out the table, you have your x values and you have your function values, your y values, right? But remember how we wanted to actually split these up evenly. Yeah, we wanted to say, okay, I want these trapeziums, I want them to be equally spread across, right? So if I'm going from 1 to 5, I'll draw this out because I think it's helpful to look at visually what's going on here, right? So this is 1 on x, it's your hyperbola. And you're going from 1 to 5. Right? And I want to split this up into 4 trapeziums, so they need to be equal lengths here. And the way I said that we can do that is we can just do b minus a on n, right? So if I take these and I subtract them, so 5 minus 1 gives me 4. How many subintervals do I want? I want 4 of them, right? So I'm basically doing 5 minus 1 divided by 4. What's that just going to be? That's just going to be 1, right? So basically you're saying, I'm going to split this up like so, just to give you a visual idea of what's going on here, right? So boom, 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 right? So these are the shapes that I'm using to evaluate my integral. So these are the x values I'm also going to use here. 1, 2, 3, 4, 5. And then I'm also going to put in the function values, right? That's really important. So I'm going to have f of 1, f of 2, f of 3, 4, and 5. And what's the function I'm working with? Well, it's just y equals to 1 on x. So that would just be 1, half, a third, a quarter, and a fifth, right? From this, okay, another way that they talk about this is they say using 5 function values. So they'll say, okay, use 4 subintervals, or they might say use 5 function values. They're kind of like interchangeable. So just be aware of the different terminology when we're talking about that, okay? So then, once you've got all of that, we can just put in our formula, right? You've already got your h value. That's what we were doing over here. So my integral, this one here, is going to be approximately equal to h on 2, so 1 on 2, outside of f of 1, plus 2 outside of all of these middle ones over here, right? So it's going to be half, plus a third, plus a quarter. Well, then that last one we only do it once, yeah? Luan, do you want to put that in your calculator for me?
101 over 60.
Good man, and that's the answer. 101 over 60. So that's basically saying this is an approximation to this integral here. Yeah? Does that make sense? So how did you set it up, Calum? So we've got 7 applications here. So what do we have to do first?
14 minus 0 on 7.
Yeah.
Yeah,
So how did you find the h value?
14 minus 0 on 7.
Yep. So the n is the number of applications that we have with that, right?
Yeah.
And so 14 minus 7, that's just going to be 14 on 7, that's just 2, right? And so that tells us now how we split up our table, right? So we know we have x values and function values. And so the x values are going to be from where we started here, 0, and it's going to be going up by each of these like heights, right? So each of the trapeziums, so 0, 2, 4, 6, 8, 10, 12, 14, right? Then all we have to do is go ahead and substitute these into your function, right? So I've got x is equal to 0 here. Oh, it should be t really, sorry. T and t there. So I've got 3, 7, yep, okay.
19, 39, 67.
Yep.
103, 147, 199.
199. Okay, sweet. And then, so all we have to do after that, because we've got this set up nice and easily, then we can just straight up substitute it in, right? So the integral is approximately equal to, so this integral here is approximately equal to, now what's your h value? That's 2 over here. So you've got 2 divided by 2. Outside, remember these ones, like these ones over here, you're going to be using twice because of how your trapezium's laid out. The ones on the edge, you're only using them once, right? So we've got here 3 plus 2 times all of these guys. It's a fair amount of writing. And what did you say you got, Cal? 900. 966. I mean, it's you're getting some pretty far x values, so it makes sense. Was that decimals at all? Or? Is it? Yep. Okay, cool. So it's a pretty nice approximation.